Welcome to Lesson 1, 7 Fundamental Concepts that help us discuss differential equations. We're going to consider the following 7 concepts. In a sense, we're learning to talk before we walk. We'll spend a lot of time using these concepts in future lessons to solve differential equations. First of all, what is a differential equation? What is a solution to a differential equation? What is an ordinary differential equation? And on the other hand, what is a partial differential equation? How do we determine the order of an ordinary differential equation? What is a transformation? And tied to that, what is a linear transformation? Some transformations are linear, some are not. Finally, why are some ordinary differential equations called linear and others are non-linear? Here are some examples of differential equations. First one, the derivative of y with respect to x plus 4 times x times y equals 1. This is an ordinary differential equation involving the function y of x, y as a function of x. Let's look at the second example. The second partial derivative of psi with respect to x and with respect to t plus 4xt equals x plus 2t times psi. This is a partial differential equation involving a function psi, which is a function of two variables, x and t. Third example, the second derivative of y with respect to x minus 2 times the derivative of y with respect to x plus 5 times y equals sine of x. This is an ordinary differential equation involving the function y of x. From these examples, we can come up with a definition for a differential equation. A differential equation is an equation that involves one or more derivatives of one or more functions. So now let's talk about a solution to a differential equation. A solution to a differential equation is a function that satisfies that equation. When you plug in the function into that equation, it's basically an identity. Here, we're talking about a differential equation just in one function. We can also talk about systems of differential equations where each differential equation might have involved derivatives of more than one function. We will consider that possibility later. But right now, this will be our first definition, I guess our initial definition of what a solution is. So now let's discuss what do we mean by a solution to a differential equation. A solution to a differential equation is going to be a function that satisfies that equation. As an example of that, let's consider this differential equation. The derivative of y with respect to x plus 4xy equals 4x. Here's a function that is a solution to that differential equation. Y equals 1 plus e to the minus 2x squared. How do we verify that this is a solution? We basically plug this function into this equation. We're going to calculate the derivative of y with respect to x, where y is this function of x. We'll calculate 4 times x times y, we'll add them together, and the result should be the function 4 times x. So I'm going to claim that 1 plus e to the minus 2x squared is a solution. So if y equals 1 plus e to the minus 2x squared, differentiating this term by term, the derivative of y with respect to x equals minus 4x e to the minus 2x squared. How did we get that? The derivative of a constant is 1. The derivative with respect to x of e to the minus 2x squared is minus 4x e to the minus 2x squared. We got that by using the chain rule. So now let's calculate the left-hand side of this equation. So what is the derivative of y with respect to x plus 4 times x times y? Well, we just found out that this derivative is equal to minus 4x e to the minus 2x squared. And what about this second term, plus 4xy? Well, that's plus 4 times x, and then this stuff right here is y. So if we look at this, we can see that it simplifies, because we have a term minus 4x times this exponential here, plus 4x times that exponential here. Those two terms are going to add up to 0, and we're left with one more term, plus 4x times 1, which is just 4x. So for this particular function y, the value of the derivative of y with respect to x plus 4xy turns out to be 4x, which means that function satisfies this equation. The derivative of y with respect to x plus 4xy equals 4x. So yes, this function is a solution to this differential equation up here. Now, let's look at another function that is not a solution. I claim that y equals x cubed is not a solution to this differential equation. So let's see what happens. Once again, we're going to plug this function into this left-hand side and see if it simplifies to give us the function 4x. So if y equals x cubed, the first thing I need to do is figure out what the derivative of y with respect to x is. That's easy. That derivative is 3x squared. So the derivative of y with respect to x plus 4xy is going to be equal to what? Well, the derivative of y with respect to x is 3x squared. 4 times x times y. For this y, we'll substitute in an x cubed. And so this equals this stuff right here. But if we look at this, this is not equal to 4x, is it? Here we have a term that is basically 3x squared. This term is going to be 4 times x to the 4th power. And that is not equal to 4x. So that tells us that y equals x cubed is not a solution to that differential equation, because the left-hand side of this differential equation, when we plug in x cubed, was this stuff right here, and that is not equal to the right-hand side, which is 4x. There are two types of differential equations: ordinary differential equations and partial differential equations. We will talk mainly about ordinary differential equations. An ordinary differential equation, abbreviated ODE, is a differential equation involving a function of just one variable. So the derivatives that appear in this type of differential equation will be the types of derivatives that you saw, let's say, in Calculus 1. Partial differential equations later, if we discuss that, will involve differential equations involving functions of several variables. Functions of several variables are usually covered in later calculus courses. So here are some examples of differential equations, some ordinary, some not. First one, the derivative of y with respect to x plus 4 times x times y equals 4x. This is an ordinary differential equation. It involves a function y as a function of x. Here's another one. The derivative of x with respect to t equals 4x. In this case, this involves a function x of t, x as a function of t, and it is an ordinary differential equation. If we have an equation like this one with a partial derivative in it, this is a partial differential equation because it involves a function of more than one variable, in this case, psi of xt. In this set of lessons, we will talk mainly about ordinary differential equations, ODEs. Let's talk about the order of a differential equation. The order of a differential equation is equal to the highest order derivative occurring in the equation. If we look at this first example, it has a first derivative here and no other derivatives. So this is a first order ordinary differential equation. This second example, we have the first derivative of y with respect to x, but it's squared. So this involves the first derivative of y with respect to x. Here's a y, which I guess we could consider the 0th derivative of y with respect to x, and no derivatives here. Since this has a first derivative, even though it's squared, this is still a first order ordinary differential equation. This last example has a second derivative here and no other derivatives, so this one is second order. If we had another term here with a first order derivative, the derivative of y with respect to x, this thing would still be second order because this would still be the highest order of any derivative in the equation. Let's look at an example problem that involves an ordinary differential equation plus what are called initial conditions. Certain Toyota Siennas can go from 0 to 60 miles per hour in 9 seconds. Assuming such a vehicle is at rest at time t equals 0 and then accelerates as fast as possible, we're assuming that as fast as possible is given by this 0 to 60 in 9 seconds up here, and that acceleration is constant. Starting with 0 velocity, how far does the car travel in those 9 seconds? Well, first of all, let's convert 60 miles an hour to feet per second. So 60 miles is equal to 60 times 5,280 feet. 1 hour has 3,600 seconds. When we do this arithmetic, we get 88 feet per second. So 60 miles per hour is equivalent to 88 feet per second. That means that if we look at velocity equals acceleration times time, that 88 feet per second is equal to the acceleration times the 9 seconds it took to get that velocity. Dividing both sides of this equation by 9, we get that a is 88 over 9 feet per second. Acceleration is measured in things like feet per second or miles per hour, that sort of thing. Well, in that case, let's see what we can do with this. The acceleration, remember, is the second derivative of position with respect to time. So if we let x be the position of the car, a is going to be the second derivative of x with respect to t. That's equal to 88 over 9. We will assume that the car starts at position 0 on a number line. Number line is measured in feet. So x of 0 is 0. The initial velocity is 0 also. So here we're taking the derivative of x with respect to time. X prime of 0, the velocity is also 0. So what do we have here? This is an ordinary differential equation. It's second order. And these two extra conditions about the value of the function at time 0 and its derivative at time 0, these are called initial conditions. This whole thing together is called an initial value problem. This one only requires calculus to solve it. Anti-differentiation. We'll anti-differentiate or integrate this ordinary differential equation. So the integral of that second derivative dt equals the integral of 88/9 dt. The integral of the second derivative of x with respect to t, integrated with respect to t, is just the first derivative. The integral of 88/9 dt is 88/9 t plus some arbitrary constant of integration c1. So now what we'll do is integrate this equation. The integral of the left-hand side equals the integral of the right-hand side. The integral of dx dt integrated with respect to t is just x. X is a function of t. If we anti-differentiate this side, remembering the antiderivative of t is 1/2 t squared, the antiderivative of a constant is that constant times t. This integral is 44/9 t squared plus c1 times t plus another arbitrary constant of integration, c sub 2. Now, we have initial conditions. X of 0 equals 0. If we look at this equation and substitute 0 in here, x of 0 is 0 plus 0 plus c2. So that tells us that c2 equals 0. What about x prime of 0? If we differentiate this with respect to time, x prime of t is going to be 44/9 times 2t plus c1 plus 0. So x of 0 is just going to be c1. X prime of 0 is c1, but this initial condition tells us that's 0 also. So what we've just found is that c1 is 0, c2 is 0, so x of t is just 44/9 t squared. That's what we have here. Now evaluate this at 9. Where is the car after 9 seconds? X of 9 is 44/9 times 9 squared, and 9 squared divided by 9 is 9. 44 times 9 is 396. The car has moved to a position 396 feet away from its initial position. That is how far the car traveled in 9 seconds. Let's discuss the concept of a transformation. A transformation, let's just call it L for the time being, is a function. We'll work with transformations that map functions into functions. As an example, let's define a linear transformation L, and L of a function y of x is equal to 2 times the derivative of y with respect to x plus x squared times y of x. Using this definition, suppose we let y of x equal the function x cubed. Then, by this formula up here, L of x cubed is 2 times the derivative with respect to x of x cubed plus x squared times y of x, which is x cubed. So here we get 2 times 3x squared, which is 6x squared, plus x squared times x cubed, which is x to the 5th. So L, in this case, maps the function given by x cubed into the function 6x squared plus x to the 5th. The domain of a function L, at least the ones that we're going to be looking at for some time, is going to be a set of differentiable functions, just like in this example, x cubed is a differentiable function. And the range of L, the things that we get as outputs from L, like this 6x squared plus x to the 5th, is also going to be a set containing functions. So we defined a transformation. Now let's define what we mean by a linear transformation. A linear transformation is a transformation that satisfies two properties. And the properties shown down here are what? For all functions y1 and y2 in domain of L, and for all constants c, L of the function y1 plus y2 equals L of y1 plus L of y2. Also, L of a constant times a function y2 is just that constant times L of y2. We want these two properties to hold for all choices of functions, which we'll denote in this case by y1 and y2. Also, from these two properties, we can show that L of a linear combination has the following property. If a and b are constants, then L of a times y1 plus b times y2 equals a times L of y1 plus b times L of y2. So, Linear transformations are transformations that satisfy these two properties. Our first order linear differential equations are differential equations that can be written in terms of a linear transformation, as we will see. We want to talk eventually about linear ordinary differential equations. In order to understand what a linear differential equation is, we first need to understand what a linear transformation is. So, we're going to look at the following fact, which will help us with differential equations later. If I define a transformation L applied to a function y, this will be y as a function of x here. L of y will be the derivative of y with respect to x plus p of x times y. I claim that this L here is a linear transformation. So we have to show two things. We have to show that L of y1 plus y2 equals L of y1 plus L of y2. And we also need to show that L of a constant times y1 is equal to a constant times L of y1. And that part I'm going to leave to you. So let's look at the first part, L of y1 plus y2, both of those functions of x. According to this definition of L, that's going to be the derivative with respect to x of y1 plus y2 plus p of x times y1 plus y2. Now, we know from elementary calculus that the derivative of the sum of two functions is the sum of their derivatives. We also know from elementary algebra a distributive property, p times the quantity y1 plus y2 is equal to p times y1 plus p times y2. So just using some properties of derivatives and the distributive property for multiplication over addition, we get this quantity down here. Now let's just rearrange terms. Let's first take this term, here it is, that involves y1. Let's pick up this second term that involves y1. Let's put it right here. We have this term which involves y2. We'll put it right here. And we also have this term that involves y2, which we'll put right here. So we have right here the two terms that involve y1, and over here the two terms that involve y2. Now if you look at this, this part right here is just L of y1. This part right here is just L of y2. So we have shown that L of y1 plus y2 is equal to L of y1 plus L of y2. The second property for linearity I will leave for your imagination. So now let's take these concepts and apply it to what we were calling a first-order linear ordinary differential equation. dy dx plus p of x times y equals q of x. This equation is first order because the highest order derivative is just the first derivative. It's ordinary because it only involves derivatives of a function of one variable. It does not involve partial derivatives. And it is linear because if we define L of y to be the derivative of y with respect to x plus p of x times y, in other words, if we define L to be the derivative with respect to x plus p of x function, then L is a linear transformation. So, a first-order linear ordinary differential equation can be written in the following form. The derivative of y with respect to x plus a function p of x times y equals q of x. P of x and q of x are functions of x in this case. This equation can also be written more or less in the form L of y equals Q of x, where L is a linear transformation. This stuff right here represents L, and it's being applied to y. So how do we apply this expression to y? Well, we do it more or less term by term. We're going to have the derivative with respect to x of y plus p of x times y equals q of x, which is exactly the same thing that we have up here. So when we apply this first term to y, we're just basically finding the derivative. When we apply the function p of x to y, the operation is actually multiplication. This equation, written in another notation for derivatives, can be expressed as y prime of x plus p of x times y of x equals q of x. This makes it very explicit that y is a function of x. For some examples of first-order linear differential equations, equations that can be written in the form the derivative of y with respect to x plus p of x times y equals q of x, let's look at these. First, the derivative of y with respect to x plus 2x times y equals e to the x. This is definitely first-order linear differential equation. The p of x is 2 times x, and the q of x is e to the x. As another example, let's look at this differential equation. The square root of 1 plus x cubed dy dx plus 3x squared y equals sine of x. What we can do to get it in the form that we have up here is to divide both sides by the square root of 1 plus x cubed. When we do that, we get the derivative of y with respect to x plus 3x squared over 1 plus square root of 1 plus x cubed y equals sine of x over the square root of 1 plus x cubed. So in this one, we have the derivative of y with respect to x plus p of x times y, where the p of x is 3x squared divided by the square root of 1 plus x cubed, and the q of x is sine of x divided by 1 plus square root of 1 plus x cubed. Let's look at another example. The square root of 1 plus x cubed times the derivative of y with respect to x squared plus 3x squared y equals sine of x. This differential equation is not linear. Notice that in the linear differential equation, we have the derivative of y with respect to x raised to the first power. In this one, we have the derivative of y with respect to x squared, and that makes this equation not linear. So what have we learned in this video? What do we now know? First, what is a differential equation? It's an equation that involves a function and its derivatives. What is a solution to a differential equation? It's a function which, when plugged into the differential equation, makes the two sides of the differential equation equal as functions of x. What is an ordinary differential equation? It's a differential equation involving derivatives of a function of x. What is the order of an ordinary differential equation? It's the order of the highest order derivative in that equation. What is a transformation? A transformation is basically a function. The functions that we're going to be interested in here are functions that take a function of x and map it into another function of x. X could be the variable or some other variable, but in any case, they're basically functions. A linear transformation is a transformation that has two particular properties. L of y1 plus y2 equals L of y1 plus L of y2, and L of a constant c times y equals c times L of y. We saw that some ordinary differential equations are called linear because they are related to the linear transformations that we talked about. Those that are not linear we will call non-linear. I hope that you enjoyed this presentation. Thank you for your time. Please continue with these. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.